This is the statics Zoom for Tuesday, May 5th. As always, hope all is well with you and your families. Leaving where we left on the last Zoom, we were analyzing the columns or the posts, if you will, for that deck. And we made a huge assumption that we're going to change as we get into the some more column analysis. So these are the answer key for pages 9 and 10. But what we did is we assumed that they were short columns, and that because they were short columns, they were going to fail in compression. And that's a huge assumption. That's actually the easiest assumption. So we always start out with that. And that kicks in what we call the simple stress formula, or allow simple stress, or what they call direct stress. Okay. So hopefully we just let somebody in. So again, this is the simple stress. Sometimes we call it the direct stress, load over area. In other words, whatever load was on that column divided by its cross-sectional area. It's a 5 by 5 post. It was 4.5 by 4.5, and there's your cross-sectional area or resisting area. So that's what we're going to talk about today, is when it does not fail in crushing or compression, where it's exceeding the material strength. So let's take a little quick stroll over to YouTube. And this is that great testing machine at Lehigh University, 5 million pound capacity. And so they break columns that are just a little bit bigger than the ones that we do. So if you were here at Delhi Tech, this is the column analysis lab that we'll talk about at Friday's Zoom. So I can't even keep a straight face. God, I'd love to have this thing in Smith Hall. So let's roll the videotape. Now you couldn't hear my, you could not hear my, let's see, go new share and share computer sound. You gotta hear this. Okay, so let's get this back up out of the way. Let's bring this out, and hopefully you'll be able to hear the sound. That is some wild shit, and pardon my French for saying the word wild. It's just amazing. Here's another test that I found. I thought I had it for last week, but I didn't. I'm going to run the first few minutes of it. It's a beam test, and they kind of show you some of the dial indicators that are used for the deflection. Again, a slightly bigger beam than what we deal with. This is what I wanted you to be able to read.
Like 110 to 160.
So there's that dial indicator for the deflection. And you'll start to see the crack patterns emerge, if you will. 66,000 newtons. Well, those guys can move. The strands of the cables. Damn it. Ice. Sweet. Okay, so took a little longer than I thought, but what the hell? This is America. You can do stuff like that. So let's go back to, not that. Let's go back to the textbook, chapter 9. And a lot of this is, pretty self-explanatory. One of the, put this up here. How am I doing here? Page 438. Sorry. Oh boy, it's going to be a long day. Okay, common terms used to identify column elements: studs, struts, posts, piers, piles, and shafts. Sounds like Dan Aykroyd on the Bassomatic. Okay, so you can imagine all the different types of materials: steel, timber, concrete, masonry, used for column construction. Okay, and so let's see here. So here's where we talked about the failing in crushing or compression, where the short column exceeds the material strength. And this is where we would show you that for the labs that we did for columns, we would, we'd get, I think, a piece 2.5 inches long, 5 inches long, 10 inches long, and 20 inches long. And the very short ones always failed in crushing. It looked exactly like this, the critical load that created that crushing effect. Okay, so very short, stout columns fail by crushing, and long, slender columns fail by buckling. Function of the column's dimensions and its modulus of elasticity, okay, which is a measure of the material stiffness. And it's those huge numbers, stress over strain. So short columns, we talked about, did it again, sorry about that. Short columns, there's our direct stress formula, the actual load divided by the cross-sectional area, and we have to be less than the allowable compressive stress per the codes, okay? And so one thing we're just not going to have time to get into are design formulas, but if you were to take, say, the actual load that you know that you're going to, the column's going to see, divided by the allowable compressive stress, that'll give you the required area. It's what they call the minimum cross-sectional area of the column. You can also do that in the bending stress formula. Actual bending stress equals M over S, moment over section modulus. So if you knew your maximum moment, you knew the allowable stress, you could find the minimum required section modulus. And that's the very basic design that you're going to get into in structural theory. And then there's the buckling effect. And it makes sense that if this is a 2x6, right, its weak axis, if you will, is running this way. Its strong axis is running this way. So it's going to buckle. That's why, when you put in floor joists, we call them a 2x10, not a 10x2. You don't lay them flat. So that's just a little bit of information. And then the long columns get into what they call the Euler buckling, okay? And the load capacity of a slender column directly dependent on the dimension and shape of the column as well as the stiffness of the material. It is independent of the strength of the material, the yield stress, okay? It's independent of the strength of the material. The yield stress, in other words. So the buckling behavior of slender columns gets into this formula. It's a relationship between the load that causes buckling of a pinned end column. And you're going to get into the end connections a lot more in structural theory. We don't have the time to get into here. But we will talk about this critical buckling load, and it's a measure of, pi is a constant, modulus of elasticity, the smallest moment of inertia, right? For a 2x10, there's 2 moment of inertias. And you got to pick the smaller one. The tables in the back of the book give both of them about what we call this, the strong axis and the weak axis. And then the length, the column length between pinned ends, which is in inches. Okay? As the column length becomes very long, the critical load becomes very small, and very short columns require extremely large loads to cause the members to buckle. And if it's super short, then it's going to be crushing rather than buckling. That gets us into another, tell you what, let's do it this way. Gets us into another type of unit. We've talked a little bit about it, I think. Actually, no, we talked about the radius of gyration very briefly in chapter 6 for shape properties. Okay, cross-sectional area, moment of inertia, section modulus, you know, those type of things. So the radius of gyration is related to column buckling. Okay. And so here's another critical stress developed in a long column at buckling. Here's another formula. This L over R is the slenderness ratio. Of course, they're going to square it, but still the L over R is the slenderness ratio. And you're going to see this a lot in structural theory. And the L over R in the equation is known, we talked about the slenderness ratio. The critical buckling stress of a column depends inversely on the square of that slenderness ratio. And the L over R, the length, and the R, that's the minimum minimum radius of gyration. Eventually, we're going to get into what we call the L over D ratio. So for this, it's got two cross-sectional dimensions. It's got the wider part and the thinner part. Okay, so it's the L over D ratio is going to be the smaller dimension, the least, what we call the least dimension. Okay. Now, that takes us up to, let's go to 446, page 446. End support conditions and lateral bracing. Okay, they talk about something called the effective column length versus the actual length. And we're going to talk about let's see, can I find that? Where is that? Is that it? Highlight text. We're going to talk about a factor K. Oh God, what am I doing now? Okay. Let's see here. I wrote it down here somewhere. Yeah, it's a factor K that's used as a multiplier for converting the actual length into an effective buckling length based on the end conditions. So you're going to see these K values, okay? You're going to see these K factors which deal with the end conditions, okay? And on page 446 and 447, you're going to see different types of end conditions, whether both ends are fixed, one end is pinned, one end fixed. Eventually, you'll get into intermediate lateral bracing, right? What you've done by this intermediate lateral bracing is you have now, even though the column, say, is 20 feet, and you're bracing it at 10 feet, you've changed the effective column length, okay, based on bracing. And think of it of a yardstick. If you push down an aluminum yardstick, it's going to buckle with very little load. If you grab the middle of it, have somebody grab the middle of it, it takes a lot more load to buckle it. If you then, say, grab at a quarter here, here, and here, it's going to take even more load. Okay. So again, you're increasing the effectiveness of the column by introducing lateral bracing about the weak axis of buckling. Okay. Here's a good little picture of that. Now, that is going to tie into the analysis that we're going to do of a wood column. We're not going to get into any structural steel. We just don't have the time for it. You will dive into that quite a bit. So we're going to go up to page 474. we're going to do a analysis or walk you through an analysis of a wood column. So there's your slenderness ratio that we talked about, L over D, and it's the minimum D. Wood columns are restricted to a maximum slenderness ratio. So when we're in the lab, we calculate, we measure the column, we measure the least dimension, and then we calculate the L over D, making sure we don't exceed 50. And so in the old days, they used to say if the L over D was less than 10, it was a short column. It was going to fail in compression. Between 10 and 20, the L over D ratio between 10 and 20 was what they call the medium column. And then anything between 20 and this maximum of 50, they talk about a long, slender column. Okay. Now, you've got, the design specifications that the Forest and Paper Association puts out. We're not going to get into, actually, let me scare you with some formulas here. Take a look at these. So what we're going to do is we're going to go through some formulas where we're really compressing the information. You'll get into a lot more of it in structural theory, but we're going to avoid formulas like this and really nasty formulas like that. Okay. Now, there's a Euler critical buckling stress right here that we're going to deal with. And there's our K factor for effective length. And we'll talk a little bit about that. And then we'll get into a column stability factor based on a stress ratio. We'll talk about that. And then here's the analysis, kind of the procedure. And I figured the best way to take you through an example problem was actually give you this right here. So what you see right here, this is page 479. So I'm giving you this. Here's 478 is this table 9.3, the column stability factor. And then the problem itself is on page 479. So we're going to walk you through these calculations. You can see I've highlighted them. In the past, I would give you this would not be containing any of my highlights, and then we would work you through in a lecture. That would be, say, a homework where you had to highlight the thing. Now that we're online, that's not really working out for us. So let's walk ourselves through here and see where these numbers are. This is going to be a good, kind of a good review, if you will, for the final. The final, damn it, I was going to bring that up first. I'd like to do the final a week from tonight. Tuesday, May 12th, starting at 6 p.m. I'll probably give you a 3 or 4 hour window. I haven't decided that. Probably a 4 hour. And then that'll be the final. And then I've still got the load trace from week 7. I still got to do that for everybody. And then I'll be able to calculate your final grades. So again, the final, I think I even put that on the email that I sent out. So you're going to see column analysis on the final. Okay, so let's go to this right here. The example problem. In all of these terms, if you can walk yourself through this, it looks nasty. It's not as nasty as that other page, but it's It's not easy, but it's doable. But we'll go through each of these terms, and you're going to know already 90% of them. A 6x8, right? That is on page 480. I got to find my copy. 478. I'm cut off right there. Oh, no, I take that back. I'm sorry. Page 567 talks about a 6x8. Surface 4 sides, S4S. Surface 4 sides. Douglas fir is the type, number 1. And that from table 5.2 on page 278 of this textbook gives us an allowable compressive stress of 1,000 psi. So if we wanted to see if this was safe in compression and it was a short column, we would just take the actual load, which is 20 kips, 20,000 pounds, divided by its cross-sectional area and see if that exceeds 1,000 pounds. But we know that we have potential for buckling because the column is 12 feet long. So we know it's not a short column. The second page of this handout is JN's notes, the first 2 pages of JN's notes, where he talks about the timber formula, and this is the Euler buckling formula. Okay, this is the very basic one. It's advanced since then, so that's why we're going through this information right here. But you can see right here is what JN is talking about right here. Okay. So I hope you brought a lot of coffee because I'm not that interesting tonight. I put everybody to sleep last Monday night. That would be last night. I think I was batting 1,000. So try to stay awake, drink a lot of coffee, and this will help you for the final. There's the P actual load. P is load. We talked about table 5.2. Gives the allowable stress, also the modulus of elasticity, which is a measure of the material stiffness. If it's a 6x8, on page 557, you'll see that that's 5.5 by 7.5. Okay, 5.5 times 7.5 equals 41.25. That's its cross-sectional area. Okay, I wrote that little XS in there, cross-sectional area. This is the L over D ratio. The D, that's right there in ancient Babylonian Sanskrit, is the least dimension. Where's 12 come from? I didn't write that down. That's the actual column length. Okay, that's LE. That's the effective length. In other words, there's no bracing between there. If there were bracing at 6 foot, then your effective length would be 6 foot. What's 12 inch per foot? CF is conversion factor. So that's the conversion factor. And then 5.5 is your least dimension of a 6x8. That's a 6x8 nominal, so it's 5.5 by 7.5. So you're going to use the smaller of the two. So the L over D ratio is 26.2, which is less than 50, so you're okay. Now you need that 26.2 because you're going to burp it into Euler's equation. Okay, and here's that K factor, and that deals with, remember we just talked about that in the text, 446 to 449. That factor is 0.3 for sawn lumber. For glulam, it's 0.418. So that's just a constant. That's something that you're going to be given. It's a $5 word for a constant, to quote my good friend JN. So you got 0.3, which is your constant. E is your modulus of elasticity. And L over D is your slenderness ratio squared. What are the units of L over D? That'd be a good test question. What are the units of the L over D ratio? It's like strain. It's unitless. It's inch per inch if you want to get technical. Okay? So the way to look at this is that now all of this is equal to a little under 700 PSI, 699. The way to think about it in a very simplistic way, it's a reduction in allowable stress due to buckling. In other words, you can't use 1,000. You can't use 1,000. But we've got to go even further to look at load duration factors, column stability factors. Mr. H is going to get into this a lot more in structural theory. So we're just going to kind of wade through here a little bit. But in essence, we can't use 1,000 PSI for allowable stress when we have buckling potential. So now we have to eventually do a ratio. It's a stress ratio. So this right here, which is what we're after, is this right here. But how do we get to there? Okay, Euler buckling is 699. This is a load duration factor. And I'm just looking up let's see. Okay, and so there's a chart in the book that allows us a 15% increase in the stress above normal conditions. And that's on page 477. Just take my word for it. On this, I'm not going to test you on something like this, but you're going to see it again. So I want you to at least know that on page 477, it's a load duration factors. In other words, how long is the load going to, the snow load, if you will, how long will that be exerted on the structure? So that's going to give us a stress of 1150 PSI based on a load direction factor for snow. And then this stress ratio will give us a column stability factor. And we're going to get that from table 9.3. But we have to have the Euler stress and the load duration, the load duration factored stress in the denominator. And that's going to give us a number of 0.61, a ratio of 0.61 stress ratio. So we go over to here and we find 0.61. We have sawn lumber. It's not glulam. Okay. And for 0.61, our column stability factor, CP, is 0.506. So 0.506 right here comes from right here. We take that and we multiply it by that 1150 PSI, and that's going to give us our new F allowable, our new allowable stress that takes into account the buckling of a column. Okay. And where does this come from? Right? We had this, which is the allowable load, is equal to the, actually that should be P allowable, not P actual. So strike that out right there. That's a blunder on my part. And we take this 582 times the cross-sectional area. So in essence, once we reduce the allowable stress, we go back and use the direct stress formula, if you will, which is stress equals load over area. So area would be over here. They're just solving for actual, I gotta get a pencil. They're solving for the allowable load. So again, stress, the new allowable stress is equal to the allowable load divided by the cross-sectional area. So to solve for P allowable, A equals B over C, that gives us, we're allowed 24,000 pounds. And we had a actual load of 20,000 pounds. And so we are safe in buckling. The column is adequate. Okay, the column is adequate. So what you're going to see for the final on columns, I'm going to give you the formulas. I may give you this chart. You're not going to have to walk through all of these calcs. I may pick some calcs out of there for you to work. I'm going to give you all the formulas. You're not going to have to memorize any of them. You do have this handout, which you're able to use anyway. And I'll ask you about, I'd give you the length of a column, and I'd give you the 2 dimensions, and then I would ask you for the L over D ratio. And one of the answers would be the length, still in feet, divided by the smallest dimension, the least dimension, which would be wrong because you got to convert this to inches. I could give you the length of the column in inches divided by the greater dimension of the cross section, which is wrong because it's always the least dimension. So those are the type of questions that I can throw at you. You know, and again on Thursday, we're going to have some column data, and we'll have you calculate L over D ratios, some very simple homework that we'll probably have due, I don't know, Sunday or Monday night, so that it gets you practicing for the column questions on the final. We'll also, I don't know how much time we'll have, but we'll get into a little bit of connections. We will go back to this, and I will calculate for you the load on the, where the hell did it go? It would be the load on the ledger beam. And then we'll talk about different connections, if you will. Those we'll be able to calculate the load that, say, an expansion bolt would see versus a masonry. They look like it's a Tapcon, that's the brand name, but it looks like a sheetrock screw, if you will, only it's rated for masonry. So we'll talk about some connections. We'll talk about some welded connections. We really don't have much time to go over it, but you'll get into that for structural theory. So we're really starting to wrap things up. We've got the we have just wrapped up pretty much the columns. Went through a very basic example problem. Again, because of buckling, we're not allowed to use the actual or the allowable compressive stress. We have to reduce it based on a stress ratio, and it gives us a much, much smaller, almost half allowable stress. But all of it comes back to just knowing the units. So that's pretty much all I have. We'll talk more about the final on our Zoom. When is ours? No, our Zoom is Friday. We do Friday Zoom at 11. And we have 15 participants here. So we'll take tonight's Zoom and, of course, Friday's Zoom, convert it to YouTube so that you can walk through it. And then the other folks who weren't able to make the lecture can also take a look at it. So I don't really have any homework for you for this Friday. just keep your eye. If I do come up with some homework, I thought about maybe having you do a little research on some structural failures. But you probably got a lot of other work to do as well. We'll give you a little bit of work over the weekend, which will allow you to grab some points. And then, of course, the final is worth 15% of your final grade. So, do you have any questions before we wrap things up? Actually, I should have like a bell to wake you up, and that's more picking on me, not picking on you. But just, one thing we'll also do is probably tomorrow or Thursday, we will post another units quiz. So keep cranking those units quizzes out. They're worth 2 hourlies. They really help your average. Okay. So I guess there's no questions. Are you out there just to make sure?
I'm out here.
Yes. Yeah.
Yes, sir.
I thought I lost 15 of you. I thought, my God, what am I going to do now? So we're going to stop. Sorry about that. It's been a long day. Again, I hope all is well. And yeah, I know one thing. I can't wait to see you in the fall. This has been interesting, but enough is enough. So looking forward to that. We will stop recording for the Tuesday, May 5th Zoom Statics and Strengths of Materials. And we will see you. We'll see you Friday.